Well, hi guys. We're going to have a look at angles of elevation and depression in the area of trigonometry in this video. It's a very interesting area and very logical and lots of fun. So come on, we'll have a bit of fun together today. Okay, when we need to look up or down in order to see a certain object, our line of vision, that is the straight line of sight, the straight line from the observer's eye, e.g. you, to the object, is inclined. The angle of inclination of the line of vision to the horizontal line of vision when looking up is referred to the angle of elevation, and if you're looking down, it is referred to the angle of depression. Well, that sounds very logical, doesn't it? The angle of elevation is measured up from the horizontal line to the line of vision, e.g. have a look at that. Here's you, and here is the horizontal line of sight, and here is the angle through which you have to sweep from the horizontal line of sight in order to eyeball the object above, okay? And that theta, Greek symbol theta, angle theta, is the angle of elevation from the horizontal. Okay, that makes complete logical sense, doesn't it? Now, just going on from that, the angle of depression, on the other hand, here's you again now. You might be on top of a cliff or something like that, or at a lookout point. The angle of depression is looking down from the horizontal line of your sight to the line of vision in order for you to eyeball the object below, which is a boat in this case, okay? So the angle of depression through which you have to sweep from the horizontal line of sight downwards, there. That theta in that case is called the angle of depression, depression denoting down, and up here elevation denoting upwards, okay? One more thing, then we'll get into some examples. Now, for two objects, A and B, okay? Now, the angle of elevation of B as seen from A. Now, have a look at this, look. See, here's A. Now, here's the angle of elevation of B. It's theta, right? The angle through which you have to sweep upwards to be able to sight B. This angle here is equal to the angle of depression of A as seen from B. See, here's if you were at B now looking down at A, you'd have to sweep through exactly the same angle downwards, theta downwards, to be able to see A, as you would have to sweep through upwards from A to see B. So these angles here, these thetas are equal, and it's a kind of a theorem of parallel lines. If this is a horizontal line, that's a horizontal line. This thing, if you studied parallel lines in, say, year 8, this would be called the transversal, and they would be called alternate angles, like the Z. They're in the Z, in the crook of the Z. Here, that's a backwards Z, but still, it's like Z for Zorro, you know, or something like that. They're called alternate angles, all right? And this angle equals that angle. All right, now we better get moving and do some examples now. Okay, from an observer, the angle of elevation of the top of a tree is 50 degrees. If the observer is 8 meters from the tree, find the height of the tree. Now, ladies and gentlemen, the first thing you must do is draw a diagram, always. So pardon my artistic lack of skill, but this should do it anyway. Now, here's our 50 degrees. That would be you there. That would be your eyeball there, okay? There's your horizontal line of sight. You must be on the ground, I presume, lying on the ground, and there is the top of the tree there, okay? So we're trying to work out the height of the tree, this H. I've called it H over here. So if we make a nice little triangle, which this will be a right angle triangle, because presumably the tree grows upwards, which they always do, we can work out this one here by using the appropriate trigonometric ratio. Okay, so which ratio would it be, guys? Well, you've got to do this side here because you need this one. You know this side here, so we'll involve this one. And you know this angle here, so we will use this angle. Okay, so that there, kick the football out from the goal, that there is the opposite side. Yes? And this one here, the next door side, the side next door to this angle, but not the hypotenuse, is this one here, which is called the adjacent. Therefore, we're going to use opposite and adjacent, which gets us tan. Okay, tan of 50 degrees is h over 8. Now all we have to do is solve that with some algebra for h. Therefore, h is 8 tan 50 degrees. Yes, of course it is. And you can look up tan 50 degrees on your calculator and you will get to 2 decimal places that h is 9.53 metres. Quite a big tree. A nice tree, eh? Probably one in a park or somewhere like that, but not in a backyard, I wouldn't think. So let's have another example here and we'll see how we go. This one looks like an angle of depression one, doesn't it? Wow. So what do we got here? The competitors of a cross-country run are nearing the finish line. From a lookout 100 metres from the track, this beastie here, that's the lookout. So someone is looking down. The angles of depression of the two leaders, Nathan and Rachel, are 40 and 62 degrees respectively. Now you better make sure you get each of these bodies right. Which one's Nathan and which one's Rachel? It's the respectively that does it. So it means that Nathan has got an angle of depression of 40 degrees. Rachel has got an angle of depression of 62 degrees. So if you follow that, you can work it out. Which one's which? How far apart are the two competitors? Well, yes, that's what I think. See, 62 degrees is this one here. So therefore, that one must have been Rachel, okay? And the other one with a 40 degree angle of depression, that must have been Nathan. So we go down here. There's Nathan. Hello, Nathan. So we're going to work out how far apart they are. So that's this distance here. You see that? That's that distance there. All right, so let's work out how we're going to do that, guys. Well, I think we need a bit more information on the diagram. I'm going to make it into a mathsy looking diagram. Put some A, B, C's and D's on the relevant points and put some angles in. Now, remember we just talked about before when we're doing the preamble to these particular specific questions that we said that these angles, these alternate angles, were this one here, this 40 degree angle of depression, would also equal to the 40 degree angle of elevation of Nathan looking up to the person on the top of the lookout, okay? And this 62 degree angle of elevation here for Rachel up to the person on the lookout would also equal the angle of depression of that person looking at Rachel, okay? They're alternate angles because these are both horizontal. Therefore they're parallel lines, okay? That's pretty important because I want to use those angles for the triangles which I've just notated there with the A, B, C and the D. Okay, now we've got to work out a game plan now. What is the plan? What do you think we could do to work out the length of, what is the length we need? AB. It's AB, yes? Okay. Well, AB does not occur in a right angle triangle. That's the problem with AB. Therefore, I think what we could do, we have to use right angle triangles to use trigonometry. This is a right angle here. So therefore, we'd have to use this triangle here, which contains that right angle. And we could also use this big triangle here, which contains the same right angle. That would be the key to it, guys. That would be the key to it. So after thinking about that, I basically worked out that we could calculate AC here, and then BC there, in those two right angle triangles, and from those I could subtract the BC from the AC to get AB. Okay, that's my game plan. So let's do that. To find AC, alright, here we go. In triangle ACD, have a look. ACD, tan of 40 is equal to the 100, the opposite, over AC. Now doing a bit of manipulation with that, I can get AC is 100 over tan 40, which comes out to be 119.18 metres to 2 decimal places, right? Excellent, we're about halfway there. Now we're going to find BC, okay, as I said in the game plan up there, here, right. BC, now I have to use another right angle triangle here, which will be this one here, there. In triangle BCD, I can say tan 62 is 100 over BC, and therefore, using the same technique as I did above, BC will be 100 over tan 62, which will get us 53.17 metres, and that's pretty good too. Now, we can now say, therefore, AB must be AC minus BC, which gets us 66.01 metres to 2 decimal places. Okay, what have we got here? We've got a 2.05 metre tall man standing in front of a street light 3.08 metres high, and he's casting a 1.5 metre shadow. In part A, what is the angle of elevation from the ground to the source of the light? And in part B, how far is the man from the bottom of the light pole? Alright, well here's the diagram which was provided to us with the question. So we've got the man here, there's the shadow there, and here is the light pole here, and there is the light, and there is the source of the light just skimming past the man's head there, and that there is the first light that basically gets to the ground, which is unobstructed by the man's body, which is therefore the shadow that's cast. Okay, that's the shadow that's cast because of the light that can't get to the ground because the man's body is in the road. Okay, that's what causes the shadow. That makes sense, doesn't it? Okay, but I think we need a two-dimensional clear diagram from which to work, because three-dimensional diagrams are always a bit confusing because right angles don't look like right angles, and etc, etc. So here's my diagram here. Okay, so I've got, there's the light pole, there's the source of the light, here's the man here, 2.05 metres high, and there is the shadow which he casts, okay? And there, so there's the light source I've showed you, there's the man. And basically, I'm going to call this angle of elevation theta, and I'm going to call the distance of the man from the base of the light pole, from his foot to the base of the light pole, x. Okay, now let's go for this. We need a game plan. To find theta and x, first of all, I think theta is pretty easy to find because we could use the small triangle C to E to D with the right angle at the base here, there. To find theta using which trig angle, guys? Which trig angle would you use? I would use tan the man, because it's the tan of theta would be this one, opposite, 2.05, over the adjacent, which is 1.5. So find theta from angle C to D to E, and then use that information in part B using the larger triangle, A here, A, B, C, because theta is also in common to that larger triangle, and that larger triangle, A to B to C, is an identical triangle in shape to this one here, to D to E to C, because they're both right angle triangles. They both have theta in them in common, and they're absolutely identical in shape, therefore they have the same trigonometric ratios. They're what's called similar triangles, scale models of each other. Okay, so in the larger triangle I can use the theta which I found from the smaller triangle in part A to find BC, this length here, knowing the 3.08, the height of the light pole. I can find BC because I know theta and I know that. Therefore I can find x by subtracting the 1.5 away from whatever I get for BC. Okay, here we go. That's the game plan. Here comes part A. So in triangle CDE, I know that theta is the angle whose tangent is 2.05 over 1.5. Okay, and therefore that comes to 53.81 degrees to 2 decimal places. All right, and I worked that out on my calculator. There we go. Thank you, Mr. Box. And in part B, I can say that in triangle ABC, the big one, tan theta equals AB, this beastie, over BC, which is the horizontal length from the pole to where the man's shadow ends. Okay, and therefore we can say that 2.05, that was 2.05 over 1.5 is what tan theta was in the small triangle, but it doesn't matter because the ratio will be the same in the large triangle. Okay, the trig ratio of tan theta will be the same in the small triangle as it is in the big triangle, so we can use just that ratio, no problem, in the big triangle, because it'll be the same. Equals 3.08 over BC. Now, just to make that a little bit easier to solve for BC, we can flip that fraction, the fractions. There's only one fraction either side of the equal sign there. Therefore we can flip them upside down if there's only one fraction and no other terms on either side of the equal sign, and we can do that. Now we can multiply both sides by 3.08 and we can get that, which is what BC is, which is 2.25 to 2 decimal places. And we're nearly there, guys, we're nearly there. Therefore we need x, and therefore we can say that therefore the 1.5 metre long shadow plus x comes to BC, which is what we just found to be 2.25, and therefore by subtracting 1.5 from both sides, we get x as that, and therefore x is 0.75 metres, 0.75 metres, and that is the distance from the man's foot, or e.g. the man from the light pole. Okay, and that's the answer. So, we'll see you next time. Thank you for coming to see me today, and have a wonderful day.